So the reciprocal of a function is a function you get when you take some other known function and just flip it under 1, literally the reciprocal. What that does is it takes all of the y coordinates from your initial function and flips them over so that they're now 1 over y, right? The point 1, 2 would become 1 over 2. The point, let's say 5, 10 would be 5, 1 over 10, for example. If you know these properties of the initial function, we immediately know some properties of its reciprocal, which makes it simple to graph. First thing, if you know the zeros of your function, when you take the reciprocal of 0, well, that's not allowed, it's undefined. And for that reason, we get vertical asymptotes anywhere that your initial function had zeros. Anywhere your initial function is increasing, its reciprocal will be decreasing. The larger a number gets, the smaller its reciprocal is, right? The reciprocal of 2 is 1/2, of 10 is 1 over 10, 100, 1 over 100. The larger a number, the smaller its reciprocal. And vice versa. If a function is decreasing, its reciprocal will increase. This one is the one that doesn't change. Wherever your initial function is positive, it will remain positive. The reciprocal of a positive number is still a positive value, and the reciprocal of a negative number is still a negative number. Another useful trait, if your function has a maximum at the coordinates x, y, your reciprocal will have a minimum at the coordinates x, 1 over y. Once again, all the points flip over. Where your graph has a minimum, it will have a maximum. One last very important property, every single reciprocal function has a horizontal asymptote y equals to 0. That sort of makes sense. As x approaches very large values, your graph will be approaching very small values. We've already mentioned the reciprocal of very large numbers gets very small. The reciprocal of a number like 1,000 is 0.001. So we have two examples here. First up, the reciprocal of a line. So sketch this line and its reciprocal on the same axes. This is a line with slope 1 and y-intercept -3. So there's the y-intercept, over 1, up 1, over 1, up 1, etc. So we end up with a line with a y-intercept at -3, an x-intercept at 3, and that's always increasing. So going through the properties we've just discussed, zeros become vertical asymptotes. So where this line had an x-intercept or 0, the reciprocal, the blue graph, will have a vertical asymptote. This graph is always increasing, therefore the reciprocal is always decreasing. It's heading down as we move from left to right. Where this function is positive, the line, its reciprocal remained positive, right? Above the x-axis, above the x-axis. Where our function was negative, the reciprocal is also negative. This doesn't have a max or min, so its reciprocal doesn't either. And note that the reciprocal has horizontal asymptote y equal to 0. As x goes on, this is going to get closer and closer to the x-axis, but never touch or cross. So now the reciprocal of a quadratic function. So this is a parabola. It has vertex down at 0, -4. It's the base or parent function shifted down 4. There's the vertex. This has zeros or x-intercepts at 2 and -2, right? 2 squared take away 4 is 0, and -2 squared take away 4 is 0. So there's the vertex, and there are the zeros, and we know that it's opening up because it hasn't been flipped. There's no negative in front of the x squared. Let's go through our properties. The zeros become vertical asymptotes. The reciprocal graph always has horizontal asymptote on the x-axis, or y equals 0. Where this graph is positive above the x-axis, the reciprocal is positive. Over here as well, positive, positive, and where it's negative, the reciprocal is negative. Where my graph is decreasing, the reciprocal is increasing, decreasing, increasing, increasing, decreasing, increasing, decreasing. And finally, the minimum that we had here down at -4 turned into a maximum at the reciprocal value, -1/4. Now let's take a look at rational functions of the form f of x over g of x, where each of these is a polynomial. So we're going to do a polynomial divided by some other polynomial. In order to sketch it, we're going to want to find the properties of the graph. First one is the zeros or x-intercepts. A rational function will have zeros where the numerator is equal to 0. So to find the zeros of a function, set the top, the numerator, equal to 0, and solve for x. Next, to get a y-intercept, no different than any other function, set x equals to 0 and solve for y. Now some new properties. Holes. A hole occurs on a graph when you're able to factor out some common factor in a rational function. An example will make this clearer, but we will get a hole at some value if the factor cancels out from the top and the bottom. Next, vertical asymptotes. Those occur anywhere the denominator equals to 0 after you've simplified. So you may get a hole, and if you cancel it out, it's not a vertical asymptote, but a hole. Whatever you do not cancel out in the denominator is a vertical asymptote. And lastly, the trickiest one, a horizontal asymptote. What we're going to do to find a horizontal asymptote is evaluate our function for very large values of x. Another way of thinking of the horizontal asymptote is the end behavior. It's what happens as x gets very large in both directions. Again, an example will make that clearer. So here I have some rational function, x squared minus 9 over x plus 3. So first we simplify. That numerator is factorable. It's a difference of squares. It factors into x plus 3 times x minus 3. Here you can see that we are going to get a hole. You can cancel out the common factor from the numerator and the denominator, and this function simplifies to this simple linear equation, x minus 3. But remember, we still have this restriction. Just because the factor canceled doesn't mean that x can be negative 3. We still have a restriction there so that the denominator never equals to 0. But again, we canceled it, which means it's a hole. This is just a line with y-intercept at negative 3 and slope of 1, there it is. But if you look over here, where x equals to negative 3, where we said there's a restriction, we get a hole. So the graph is a normal line, except when we reach negative 3, it just hops over that one little point and continues onward. So now neither of these are factorable. Can't pull anything out here, can't pull anything out there. They have nothing in common, which means this graph will have no holes. Nothing cancels out. So let's go through the properties. To get my zeros or x-intercepts, I set the numerator to 0. When does 2x minus 9 equal to 0? Solving that, I get 9 over 2, or 4.5. Next, we can get a y-intercept. Y-intercepts occur when x is equal to 0. Setting x to 0 in my function, I get negative 9 over 3, or negative 3. Now the asymptotes. Vertical asymptotes occur when the denominator equals to 0. So setting the denominator to 0, I find I have a restriction at negative 3, and that restriction will be an asymptote. And now this tricky one, the horizontal asymptote. An easy way to find it is to simply plug in a large value of x. See what's happening as x is getting very, very big. I plugged in 1,000, just to get an idea. If you simplify this, the numerator will be some number just below 2,000. 2,000 take away 9. And the denominator will be some number just larger than 1,000. The larger that you plug in this value, the bigger the number is, the closer your number will be to 2. You may get 1.999 or perhaps 2.001. You're going to get values very close to 2. So we conclude that the horizontal asymptote is 2. As x gets bigger and bigger, my function is tending to the value 2. Putting this all together, there's my vertical asymptote at x equals negative 3, my horizontal asymptote at y equals to 2, my y-intercept at negative 3, my x-intercept at 4.5. Now remember, the definition of an asymptote is a line that your function gets closer and closer to, but never touches or crosses. So now I can piece together this segment of my graph. I know it has to pass through the intercepts and tend toward the asymptotes. If this kept going on, it would be getting closer and closer to the asymptote. There's another section to this graph just to the left of negative 3. It's going to be up here. If you're not entirely sure where the graph is going to be, we can always just find some accuracy point, just plug in a value for x and figure out whether it's going to be above the asymptote or below the asymptote. We could try plugging in, say, negative 4. If you did that, you'd find that you're up in the positives, which means your function is positive and tending toward infinity that way, and then down toward 2 that way.